Recording is rolling. It is Thursday, January 23rd. Okay, so just finished rotational dynamics. Here's top scientists for rotational dynamics. I got three different top scientists lists. So here's the AP Classroom Unit 5. Here's the AP Classroom Unit 6. And here's your rotational dynamics quiz. Okay, so awesome job if you made any of those lists. Okay. We are moving on to next topic, which is going to be simple harmonic motion. Right, so you guys have new thumbnail notes. Gave you guys the spring version of these. I printed these out over the break a few weeks back. So you guys got a few pages of new topics here. Right. Some of these topics don't show up on the AP exam, but I might cover them briefly just to get some exposure to them. But some of these do. Right. Actually, the orange banners on front are fluids, which we're not doing right now, but we're doing simple harmonic motion, which it's buried in there somewhere. Okay. All right. So you guys got those. All right. So you guys got some materials on your desk today to do a pendulum lab, including this page here. All right. So do you guys see? Oh, do you guys write your name on this? Everybody write your name on the table page. Okay. All right. So there are three tables here. I'm setting up three experiments for you guys. And on the back side are set up four sets of axes because we're going to do four graphs altogether. Right? Actually, before I forget this, forget one thing. Do you guys see this lexicon on your desk? Right, it'll rotate like this. So this is a bridge activity I did with my other classes, so I could keep them all on track, so we could do all pendulum labs same day. Okay. If you want to make one of these, I did post the video for my other classes to Google Classroom, so you guys can see the directions. If you want to keep the one on your desk, then you can. So those are the ones on your desk, just some extras that got left over. All right. So as we're focused on this pendulum lab. So, all right, back to that. You guys see I got a pendulum going on right here? Got a string. I got a mass here. Ooh, guys, do you guys think that almost all the mass in this pendulum is in this bob in the end? And maybe the string could be called negligible mass, you guys think? All right, all right. And that'll be applicable to this class. Okay. There's a fancier version where there's significant mass in the string here, but we're not going to really focus on that one so much, right? So all the mass is going to be considered to be in this bob, right? Hey guys, do you guys see it takes some amount of time to go back and forth once? I'm going to define the amount of time to go back and forth as one time period. And that'll be capital T. So here, let's see if you guys are following. Guys, is the time period from the left to the right, or is the time period from the left to the right back to the left again? Which one's the correct time period? The second thing I said, right? From the left to the right and back to the left again. Right? However much time that is. You guys got stopwatches on your desk, right? Well, I bet there's some laws of the universe that are going to govern how much time that is. All right. Because what variables can you think might possibly, like, reasonably go into that? What's one variable? Okay. So I heard two of them. I heard possibly the mass. All right. So maybe this mass could be treated as a potential variable. Maybe the gravity field. Now, the gravity field, we can't really change this class. It turns out it does show up in the equation. Let's do a quick thought experiment. Guys, gravity field. If this was on the moon, where there's really weak gravity, there's a little bit of gravity, but not, right? Would this swing back and forth really fast or really slow? I bet really slow. I bet on the moon it would be like, right. Well, without the sound, because no sound on the moon. All right. What guys? What about I bet yeah, we can't really test for that in this class, right? How about this mass? Let's talk about that since that was proposed as a potential. Right, guys. What if I replace the small mass with a bigger mass? Or I got some smaller ones too. So as I increase the mass, make it bigger, bigger, bigger. Okay? Put kind of an order to these. As I make the mass bigger, 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 is that gonna increase the time period, which is say it slows down? Is it gonna decrease the time period, which say speeds up, goes back and forth really fast? Right? Or would it be no change? Let's do a quick hypothesis. How do you guys think as I increase the mass, it's going to also increase the time period and slowing it down? Right? Who thinks as I increase the mass, it's going to decrease the time period, like speed it up? Okay? And who says that as I change the mass, it's going to swing back and forth the same, like no change in time period? Okay. Oh, okay, so I'm seeing hands raised for all three of those hypotheses. Right, so hold on to those, right? Because one of those would be correct, right? Okay. How about guys? What's another potential variable that could determine the time period?
Length of the pendulum.
Length of the pendulum? Yeah, length. Right. Right. So if this is really short, or if this gets longer, 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 if I let out more string, it'll get longer, longer. Right. So let's say the same three hypotheses. So who thinks as I make the string longer, it's going to increase the time period, say slow it down? Who thinks as the pendulum gets longer, it's going to decrease the time period, which would be like swing back force faster, right? Call it decrease frequency. And who thinks as I increase the length, it makes no difference at all, right? All right. Now, whichever one of those is correct, like if there is a change, then you could go further and say, well, what exactly is that change? Like if I double the length of the string, does that double the time period, or does it more than double or less than double? Right. Okay. See, it's the same type of relationships we've been working on like all year. Guys, what's another variable that can matter? I'm thinking of one more. Yeah, this initial angle from the vertical. I like you said, an initial angle, right? Because of course the angle is always changing as it swings, but maybe the initial angle from the vertical. Didn't I draw this from the vertical? Like glance at that, you think that might be about 20 degrees or so, right? And you guys have protractors, so you can actually measure and quantify that. What's the initial angle, right? And then let's do some quick hypothesizing. As I make that angle bigger, 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 is that going to increase, decrease the time period, or no change at all? Who thinks as I make this angle bigger, it's going to increase the time period? Who says that? Who thinks a bigger angle is going to decrease the time period? And who says a bigger angle makes no difference at all? Ooh, all right. I think I'm seeing votes on every one of those hypotheses. All right, so yeah, let's really open-ended lab. Like anything can be true. You guys gotta find out. Okay. All right. You guys good so far with the premise? Okay. All right. So since you guys are AP, I'm also having you guys complete an AP style write-up. Now this you have to do on a separate piece of paper. You can do your own paper, or you guys know I always have paper on these stools in the middle of the room. So if you need to get some paper, there's always paper there. Okay. And I gave you guys one of these square pages to remind you guys how to make an AP style write-up. If this was a free response, guys, this could totally be your FRQ sitting just waiting in May, just waiting for you right now. Right? Of course, they'll prompt you step by step. Right? So that's why I can give this to you. Right? But it's kind of good to be familiar with it. Right? So this is on your desk. Right? And we're really going to do 3 different experiments, and it's the ones we just did hypotheses for. Right? So we're going to relate everything to time period as you change this mass, as you change this length, as you change this angle. Okay, so it's 3 experiments. I see 1, 2, 3 tables. Do you guys see 3 tables to go to 3 experiments? I see that, right? And I did as much as I could on a page. So really, ideally, maybe you'd want to do like 3 trials per mass or 3 trials per length or something. Okay, before you change the mass or change the length. Okay. Okay. Of course, we got to do 3 experiments for 3 potential independent variables, so you can control the other 2 at the same time. Right. Here's what I want you guys to do for the write-up, just so we're all on the same page, just to make it a little bit uniform. Only do the write-up for treating the length as the independent variable. Okay. And if that's true, then are you changing the mass? No, that would be controlled. Are you changing the starting angle? No, that would be controlled. Right. That's specific to the write-up I want you guys to do. Okay. So when you guys do the write-up, have this specific experiment in mind, which is going to correspond to one of your tables. You guys get that? Right. So you do 3 experiments. You get a whole, 3 tables of data, but you're only doing the write-up for one of them. Okay. Right. You guys get so far? Right. And here's the goal we're headed towards: is time period equals. We're looking for some formula that's going to govern the motion of that pendulum. Okay. How much time? Right. You guys get that? Okay. Now I'll help you guys out with this table a bit here. Right. So you guys did write your name here, right? You guys write your name. Right. This is Pendulum Lab. Right. You guys can use gravity field. Actually, I don't think this matters too much. Right. We're just looking for proportional relationships. So maybe I'll have this in the back of my mind, but just we're kind of locked into that. Right. So really, we're just headed for proportional relationships. Call this Pendulum Lab. Pendulum Lab. Right. Pendulum Lab. Right. Right. You guys see you have 3 tables on one side. You guys have spaces for work towards 4 graphs on there. We might not get to the graphs until tomorrow. Probably makes sense, right? Right. So you guys know what these tables look like. There's variables and there's units. Guys, what's one variable you told me to throw down? Okay, I heard mass. Tell you what, let's treat gravity as you can put G in here if you want to. I create some extra columns. I'm not going to so much focus on gravity. That'll just be controlled either way. Okay. But there's mass, and what do you want to measure mass in? You can go grams or kilograms. I'll leave it up to you if you want to use grams or kilograms. Okay. You guys know the base SI unit is kilograms. Okay. Maybe we'll say. Okay. But these lab acids are really tiny. So, what's another variable? Yeah, length, and that could be in what unit? Yeah. So I heard centimeters. I heard meters. Again, up to you guys what you want to measure in. It's up to you. Okay. Regardless of the unit, the proportional relationships will turn out the same. If you're looking for exact equations, might be safer to tend towards space SI units. Okay. And what's another variable? Starting angle, right? And that can be measured in what? Degrees would be pretty good, right? Degrees, right? Okay. If that shows up in the formula, I'm gonna guess maybe it shows up inside a sine or cosine if it shows up at all, or right. Because if it did not show up inside a sine or a cosine, then you actually you would want to use radians, wouldn't you? Right. Okay, so be careful about that. If you directly multiply the angle, actually this would have to be in radians. Right? Maybe the fact that I'm giving you degrees says something about that. Right. What other measuring tool do you have on your desk? Ooh, stopwatch for time period, right? Right. Now, guys, think about how you measure time period, especially for something oscillating back and forth. Should you try to nail it in one oscillation, or is there a better way to do it? Yeah, yeah.
And then divide it, average.
There you go. Yeah. So here, take. What if you let go back and forth like 10 oscillations, right, and divide by 10, right? Or 5 oscillations and divide by 5, right? Because, and here's why. Here's why. If you just let it go back and forth once and you try to hit start, stop, do you think there's some error, reasonably, there's some error in figuring out where to stop it, right? Say you're off by like a half a second, right? Then your graphs are going to be totally messed up and it's really icky, right? But if you let it go back and forth 10 times and divide by 10, and say you're still off by half a second, does that half a second of error also get divided by 10?
Yep.
Ah, right. Yeah.
But doesn't it get like take less time every time, and so then you're just taking the average of length?
Ooh, that's a good thought too. Here, is it constant? Say time period or constant frequency over 10 oscillations, or does it slow down? Okay. You know what? I'll let you guys hold on to that question too, and maybe you can find a way to measure that. Yeah, so try that out. Okay, let's swing back and forth. Suppose it does 15 oscillations, and you do the first 5 and the middle 5 and the last 5, and you kind of keep track of, is it slowing down or is it pretty constant? Huh. All right, I'll let you guys figure that out. Okay, right. Right. Oh yeah, what's here?
One oscillation is one.
Yeah. So remember, one oscillation is from the left to the right, back to the left again. Yeah, that's one full oscillation. Yeah.
Do 5 oscillations for a thing, or do we have to do 10?
Yeah, you can do 5. Okay, all right. So kind of leaves up to you. Right. Just in your when you do a write up, just specify how many oscillations you did. 5 is fine. Okay. Okay. So I have not finished the whole table. There's some more stuff you want to write. Okay. Now, guys, these 3 different experiments, you're working with the same sets of variables and the same sets of units. Right. But you're treating some of these as independent variable and some of these as controlled. Guys, how many independent variable at one time? 1 independent variable and 1 dependent variable, and everything else is controlled. Right? Right. All right. All right. All right. So, all right. I think I told you everything you need. All right. So go ahead, get all your data for those 3 different experiments today. If you can get some graphs going, then go ahead. But this is my first class today, so you guys are kind of setting the pace. And we're probably gonna have to finish working on this tomorrow.